Here, another application to Gauss's law. We have a long cylindrical charge distribution of radius capital R with a uniform charge density rho. It means we have a volume charge density, okay? And we don't have a conducting or metallic object. So in this case, the charge will be totally uniformly distributed inside the object. So we can say here, in general, Q equals to rho times V. Let's draw the cylinder here. This cylinder has a radius equals to R. Here we don't have a shell like the last example problem. We have a cylindrical object. It's full, it's not empty, okay? We have a charge at any point inside the body of the object. Here we have to find the field at a distance r, where r at a distance small r, where the small r is less than the capital R. We have to find the field at any point inside the cylinder, okay? In order to solve this problem and to calculate the electric field, you know, we have to apply Gauss's law. Be careful here. We have a long cylinder. It's not small. When we say it's a long cylinder, it means it's long to the infinity, okay? It's not limited. So we can say here the length of the cylinder goes to infinity, up and down, up and down. You know, in the case of a cylinder, when we solve and we use Gauss's law, the final formula it doesn't depend on the length of the rod. Okay. Okay. Let's calculate the field by using Gauss's law. Here, you know, by symmetric, we take a cylinder of radius small r, which is less than the capital R, because we need to calculate inside as Gaussian surface. Okay, we can draw this one. So here, this one is Gaussian surface, which is at a distance small r from the center. Okay, you know, here we have dA and E is a positive charged object. Here we have E. We get, we have to say E is parallel to dA. E is a radial vector, and E as magnitude is constant at the surface. And we can write the flux equals to the integral of a closed surface E dot A equals to Q N divided by epsilon. Okay, you know, in general here, we have a positive charge at any point inside the cylinder, okay? At any point. Here's the total charge we have. So we can say the total charge Q here on this one we have a total charge Q, and Qn is located inside the Gaussian surface, okay? Qn is only the quantity of charge located inside Gaussian surface. Okay, you know, here we have a uniform distribution. Here we have a volume charge density. We can say the total Q equals to rho times the total volume of the object, and also we can say Qn equals rho times Vn of Qn. Okay. Okay, now we have to calculate this value. Let's clean. So we can write the flux phi equals to, you know, the angle between E and dA equals to 0. So cosine 0 equals to Qn divided by epsilon 0. So E is constant, we get out E. Integral of dA equals to A equals to Qn divided by epsilon. Let's calculate each value. You know, we have a volume charge density, Qn equals rho times Vn. Here, the volume of a cylinder equals the area of the disc of the section times the height. Okay, let's say here we have a height of this cylinder equals to here, be careful, the length of the red cylinder is not equal to the length of the blue cylinder. The blue cylinder has a long length. It's a long. But the red one is a Gaussian surface. It's a limited height. Let me change the height of the red one. As you see, here we have just a length L, a length, let's say H, and a length H of the cylinder. And here we have A equals to the area of Gaussian surface of this one, the red one. We can write A equals to pi r square, the area of this disk, times the height. So we get pi r square times h. Okay, this is A. And Qn equals to rho times Vn. Vn is the volume which exists inside this Gaussian surface. We can say Vn is the volume of the of Q charge of Qn. We can say the volume of the cylinder where Qn exists. Okay, Qn is inside. Here we have Qn. So we have to calculate the volume of Vn. Here we have Vn. So Qn equal rho times Vn. Let's substitute the value of Qn and A. We get the value of E. We can write E equals to Qn divided by A epsilon 0. We have Qn equals to rho times Vn, the volume of Vn, the volume of this one, of Qn, equals to pi r square times h. Okay? Excuse me. Here, A equals, it doesn't, is the volumes one. Okay? A is the area equal to pi r times h. Okay, excuse me. Here we have the area of the Gaussian surface. The area of cylinder equal 2 pi r times h. Okay, equals to 2 pi r times h. And the volume of the cylinder equal pi r square times h. Okay, so here we have rho times the volume Vn equals to pi r square times h divided by a, which is equal to 2 pi r times h times epsilon 0. We can get finally E equals to pi and pi, h and h. We can cancel. We get finally rho r divided by 2 epsilon. As you see, the final formula of E or E doesn't depend on the length of the cylinder. Okay, so in this case, we don't need to take a Gaussian surface, the cylinder as a long cylinder. We can say E doesn't depend on the height of the length, on the length h. Okay, if we take a small Gaussian surface, or we take a long Gaussian surface, this will not affect to the value of the field created at in this position. Okay, E doesn't depend on the length h in this formula, so we can choose any length of the Gaussian surface. Okay, Gaussian cylinder. Because maybe you can ask me why you take only a small cylinder as a Gaussian surface. Why you don't take a cylinder very long to cover all the length of the cylinder? Okay, we don't have a the length of the field doesn't depend on the length. Okay, this is the value of the field. So you can say at any point here, at any point at a distance r inside the cylinder, we can calculate its value. As you see, the value of the relation between E and R is linear. Each time you increase the distance, the value of the field will increase. I mean, if you increase the radius of the cylinder, let's say here we have a point A, here we have a point B, here we have a point C. We can say E at the point A is less than E at the point B is less than E at the point C, because E will increase with the radius. Each time R is bigger, E will be bigger. If you draw the relation between here, the relation between E and R, you get a linear relation between them, between 0 and R. Okay, we can say like this. Okay, thank you.